Hi everybody, this is Coach Sweeso and welcome to this video on 5.5 and 5.6. Unfortunately, I am not here today, and so I really quickly made this video so that you could have me teaching you the topics and make sure that you understand it all as we go into the weekend. They're both pretty straightforward, so it shouldn't be too much of an issue to learn it, but my recommendation is after you watch these videos, if you need more, watch the AP Classroom videos, Michael Fairbow, and read the notes, and that will help tremendously. And then, of course, do the you-dos and check them up front. Just a reminder that the OWL is due tonight. It is very short. It's like 8 questions, takes 10 to 12 minutes. It will not take long. It is an other grade, but it is due tonight. All right, let's start with 5.5, collision model. We're going to explain the relationship between the rate of an elementary reaction, which we figured out how to find yesterday, and the frequency, energy, and orientation of those molecular collisions. So remember we talked yesterday about the fact that this is at the molecular level, unimolecular, bimolecular, etc. What is actually colliding and how it's colliding will affect that rate. So now we're going to kind of really connect that to the collision theory. Remember, in order to react, a molecule has to collide. So the greater number of collisions per second, the greater the reaction rate, because you have a higher chance of successful reactions and successful collisions. As a reactant concentration increases, the number of collisions should increase, leading to an overall increase in the reaction rate. So collision theory states that in order for a reaction to take place, the following 3 things have to happen. First, your particles have to actually collide, right? They have to hit each other. If they don't hit each other, if there's no collisions, then there's no chance of successful collisions, and so then it won't take place. They have to have the right amount of energy when they actually do collide, and we call that the activation energy of that particular reaction, which we're going to tie into 5.6 in just a minute. And then your particles have to be in the correct orientation, which means they have to collide in a certain way. If they do not, there will not be a successful collision. So remember, all 3 of these things have to happen at the same time, which is why successful collisions are, particularly with bimolecular and teramolecular reactions, they're going to be slower. So activation energy, if you've got sufficient kinetic energy to potential energy, then your molecules will be able to form what we call the transition state, in which the reactant bonds are broken and the product bonds are forming. So if I'm looking at this graph over here to the right, this is my reactants, and this is where I'm starting at this particular potential energy. And then I go from here all the way up to what we call the transition state. And this is my activation energy, the energy that's required to get there. When I get there, this is where my bonds here are broken and these bonds are formed. And then we fall down to the potential energy of the product. Sometimes this transition state is also called the activated complex. So either one of those terms would refer to this spot at the top of the energy profile. So this also ties in with what we call the Maxwell-Boltzmann distribution relevance. And remember, we talked about Maxwell-Boltzmann in Unit 3. If we say that activation energy is the minimum energy required for a successful reaction to occur, so in order to increase the number of particles that have that energy, you have to heat the sample. So remember, with Maxwell-Boltzmann, this was the lower temperature, so most of the particles fell right here, but the higher the temperature, the graph moved to the right, and overall the average kinetic energy of the particles increased. So right here, this would be the minimum energy that's needed for the reaction. And you notice that at the higher temperature, there's a greater area under the curve past that minimum energy than there is at the lower temperature. But the red will have more. Now, any of these that hit each other and react, they would not react. So the successful collisions would happen in this particular little triangle down here. And then remember orientation. So if you've got this proper orientation, right? This is nitrogen dioxide with carbon monoxide. So when they react, if it orients like this, then you get your reaction products. But you notice all 3 of these, we have incorrect orientations. So they might collide, they might have the right amount of energy, but we're still not guaranteed a successful reaction because most molecules won't be perfectly oriented like this. And so again, we're trying to increase the chance and the probability of a successful reaction. So the more that collide with the proper orientation, the more chance that we're going to have our reaction products. So collisions occur all the time, but again, not all collisions will result in the reaction. So this explains, we talked yesterday about why bimolecular reactions can occur, right? Because they can collide at the right energy and the right orientation. But like trimolecular, teramolecular, so unlikely to occur, or at least it's going to occur a lot more slowly because all 3 particles combining and reacting at the right energy, at the right orientation, all at the same time is much more unlikely. So remember from 5.1, we talked about different factors from that collision theory talk about things that could increase the reaction rate. And so here they are again, just as a recap: increasing surface area, increasing concentration, increasing pressure, increasing temperature, and adding a catalyst. And remember, the way the catalyst does it is by changing the activation pathway. All right, so let's look at this together. And this one is the problem that is in your notes here. And so this is already written in your notes, but I'm just going to leave it on this slide to go through it here. It says, given the following reaction, which set of reaction conditions will result in the highest reaction rate? Explain in terms of collision theory. So if I look at all these, let's kind of talk about what we're looking at here. They're all three at the same temperature. Experiment 2 does have more moles here, so that's kind of worth noticing. However, it does have more moles, but look at the volume of the container. Okay, it's got a volume of a container that is 4 times the amount of the volume of the container of experiment 3. So we want the one that actually is going to be in the smallest container, because that means that we're going to have the highest pressure and therefore the more chance of likely collisions. So experiment 3 should result in the highest because it's got the smallest volume of the container with 1 mole of each. Experiment 1 has a slightly bigger container with 1 mole, so we know that that's going to be less, or it's going to be slower. And then experiment 2, it does have the 2 moles, but it also has the 4 for the volume of the container, which more or less puts it out of contention because that's 4 times the amount of the volume here. And then, of course, you've got this you do, we review. In order to save time on this video, just to, make sure that you have enough time to work your you-dos, I'm going to let you work this one on your own. And then go ahead and scan the QR code tonight when you have your phones to make sure you got it right. And I will go through this one on Monday. All right, now I'm going to pop on over to my 5.6. Oh, sorry, that's for last year's date. Here we go, 5.6, reaction profile diagrams. And sorry if I'm talking a little bit fast, which I probably am. I'd want to make this video as efficient for you guys as possible, but you can always, of course, slow it down, rewatch it, or watch any of the other videos that are available to you. This is just to give you, kind of the basics to make sure you don't feel like you're being left to drown or tread water here. All right, so 5.6, reaction profile diagrams. We're going to represent the activation energy and the overall energy change in an elementary reaction using a reaction energy profile. So reaction energy profiles are a way to graphically represent a reaction, and you probably know them as energy diagrams. We talked about them in Cap Chem a lot. You saw them particularly in the thermochem unit, but they also matter a lot for kinetics. So the y-axis, which is right here, is generally our potential energy, and my x-axis is going to show the overall progress of the reaction. So this graph over here shows my reactants. We saw this in the last lesson. Shows my reactants going to my transition state and overcoming that activation energy, and then it falls to my products, which are down here. So remember when we talk about thermochemistry, right? Like if it loses energy, it's exothermic. If it had ended up higher, it'd be endothermic. And we'll get into that in January, but just to tie into that unit. All right, so collision theory says, like we talked about, that a reaction has to occur between molecules in the correct orientation with a sufficient energy. So remember, this activation energy, and this is a recap, is the energy that's required for those molecules when they collide to have in order to have a successful collision. So again, we call this spot the transition state or the activated complex. So the activation energy for the forward reaction, and that means that we are going from reactants to products. So energy of activation is equal to the energy of the transition state, which is ETS, minus the energy of the reactants. So it is right here, EA. If you are going in the reverse reaction, it's going to be the activation energy is the energy of the transition state minus the energy of the products, and that is all the way down to here, which makes sense. If we're coming from the products, we have to go from this energy and overcome this much activation energy to get to the transition state. If we're going from our reactants, we only have to overcome this much, which is why some reactions are only forward facing, right? Because particularly if it's a significant difference in energy, because it's so much easier to overcome this energy, it doesn't have the energy to go backwards. This ties in with thermochem quite a bit, and we'll talk a lot more about this in January. But the enthalpy of the reaction is the potential energy difference between the products and the reactants. We know, hopefully, that exothermic reactions release energy and an endothermic reaction absorbs. So by definition, when we work that out, the enthalpy of a reaction is the products minus the reactants. If you end up with a negative enthalpy, it's exothermic, and a positive enthalpy is endothermic. And this is what those look like. So this would be an exothermic reaction, wherein when I subtracted my products minus reactants, my products are lower than my reactants, right? So I'm losing energy overall. So that would be exothermic. Here, to get from reactants up to where the products are, I have to put energy into it. And so that would be an endothermic reaction. And this is, again, kind of another review slide. But the transition state, remember, is that intermediate point between the two stable compounds. So it's when the bonds are breaking here and they are forming here. So if they can collide with enough energy, they can proceed over this bump and into the products. If the energy of a transition state is greater, the reaction will be slower because fewer collisions will have enough energy to get up this hump to go over into the products. Now let's look really quickly about a multiple step reaction, which really comes into play when we talk about elementary steps with reaction mechanisms, which we talked a lot about yesterday. Remember, elementary steps really give us a look at what is actually going on. And this is not actually directly in your notes. So my recommendation would be to draw this one or draw some sort of version of this, pause the video and put this in your notes somewhere so that you have it. So remember, the slow step is your rate determining step. When you're identifying that on a activation or an energy diagram, you're looking for the one with the highest activation energy. So it says which step would be the rate determining step in the reaction profile on the right. So my two steps are here and here, right? And so the first one has to go from the reactants all the way up. So we call that EA1. And then we fall down here. So this would be my intermediate step. So maybe the end of step 1. And then my step 2 in the elementary reaction would be right here, which this goes from here down to there. So that's a much lower activated complex. So EA2 is significantly less than this. So the rate limiting step is probably going to be step 1. You can also see each of the steps have different enthalpies and different exothermic versus endothermic. This one right here goes from reactants up to the products, so you have to put energy in for this first step, so that's endothermic. The second step going from here to here is exothermic, and it's also fast because it doesn't have a high activated complex. So second step, very quick, releases energy. First step, slower and requires energy to do. So let's talk about how temperature. Recall that rate law, right, is your rate of your reactants to their particular order. And remember we talked a lot on that first day that the rate constant, which is K, changes with temperature, which is why temperature is given to us in a lot of problems, because we are specifying in that problem that the temperature is not changing, therefore my rate constant is staying the same. Changes to temperature are proportional to the kinetic energy of the molecules. This doesn't change the overall reaction mechanism. Like when I increase the temperature, I am not changing my elementary steps and the order in which they happen. So the energy of the transition state ultimately remains unchanged. Instead, basically what K accounts for is that now more molecules can overcome that, this bump. So this would not change. It's not like changing the temperature would lower this or raise this. It just means that more molecules would now have the kinetic energy to get up there. So this is actually beyond the scope of this course, but if you are somebody that, wants to know a little bit more, this is actually at the bottom of your notes, okay, underneath that Maxwell-Boltzmann distribution. So you can, again, look at this and, take it into account, but don't stress too much about it. It's certainly not something that is tested, okay? But the value of K is dependent on what we call the Arrhenius equation, which is right here. And this is actually how it's calculated. A is our frequency factor constant, and then this species right here is always going to end up being a value between 0 and 1. And that represents the fraction of the molecules that have the amount of energy to overcome. So it basically represents these in the Maxwell distribution. And so, the higher it is, the higher percentage that your molecules will have the energy to overcome. And then finally, a catalyst will change your reaction pathway by actually lowering the activation energy. So this is where you can actually change it. So if this was a one-step reaction, we get a massive activation energy and a very high transition complex up here, and that would be a lot of energy to overcome. And there's potentially not a lot of molecules that be able to make that jump. So if we add a catalyst, all of a sudden maybe the reaction pathway now is 3 small steps that are maybe unimolecular instead of bimolecular, or instead of trimolecular, teramolecular. Like maybe it's just a little bit lower and easier to do. And so this catalyst now all of a sudden changes my activation. Boop, boop, boop. So overall, the energy might be the same as this entire piece when you add them up, but being able to do it in small steps like this, that catalyzed reaction means that it lowers the overall activation energy. So this results in what we call the multi-step reaction pathway, which is what we saw yesterday, having multi-steps in order to get to the same product. All right, let's look at the we do's and the I do's. So the first one is sketching a diagram of an endothermic reaction. Obviously, you see that on your page in front of you. The big thing there is that your products have to end up higher than your reactants, which is a fancy way of saying that when you take your products and subtract out your reactants, so products minus reactants, you should get a positive delta H, which then you see it in front of you kind of looks like this. There's a better one, obviously, in your notes, but that's how it should look. All right, let's look at the we do. It says, on the graph below, draw a reaction energy profile of a reaction with the following. So my reactants are at 20, so that's right here. Okay, my transition state is at 80, so I'm going to put that right about here. And my products are at 50, which is right about here. Now, I'm not a very good artist, but let's connect that as smoothly as we can here. There we go. And then if I'm going to label it, this would be my reactants. This is a very straightforward question here. This is my transition state or transition complex. This is my energy of activation. This is my products. And this difference right here is my enthalpy of the reaction. And there we go. You don't have, it doesn't say label, but, it's always good practice to make sure you identify your graph, particularly since you're, reviewing them. All right, if you have any questions, go ahead and jot them down. I'll be happy to answer them when I get back on Monday. Like I said, these were both pretty straightforward little lessons, but I just wanted to make sure you heard them from me. And then we'll just talk about any misconceptions when we get back from the weekend. Enjoy your weekend. Make sure you work hard for the rest of the day. Please do the you-dos, check them. And I will see you guys next week. See y'all later.